In the previous section, we learned just about everything there was to learn about quadratic functions. And remember that a quadratic function is just a polynomial function of degree 2. Well, in this section, we are going to deal with polynomial functions of degree n, where for the most part n will be greater than or equal to 3, although we may refer back to quadratics in this section as well. So first, let's just define a general polynomial. If we take a bunch of real numbers, a sub n minus 1, all the way down to a2, a1, a0, so they're all real numbers, then f of x equals an times x to the n power plus an minus 1 times x to the n minus 1 power plus, and then we go all the way down to a2 goes with x squared, a1 goes with x to the 1 power plus a0. This is exactly how we would write a general polynomial function. And this is written in the correct form, the way we like to write it. Although the order doesn't matter, we tend to want to write it in descending order of the exponent. So here's the biggest exponent. Here's the next biggest exponent, all the way down to the exponent of 2, 1, and 0. So that's a polynomial function. A0 is this guy right here. Notice he doesn't have an x with him, or if he did, it would be x to the 0, which is just equal to 1. So this is just a number. A0 is called the constant term. Okay? And then on the other end, when you get to the degree n term, an is called the leading coefficient. I might refer to that as LC sometimes, the leading coefficient. Well, let's look at a couple of examples. These are very, very small degree polynomial functions. In fact, this one is just, C is just a number, just a real number. This means this is the constant function. If you were to graph that, it would be a horizontal line, and the height of it would be relative to the x-axis. The height of it would be c. This one is linear, a linear function. This is y equals mx plus b. And then this is the quadratic, and we dealt, the entire previous section was about the quadratic functions. It's ax squared plus bx plus c. And here's a picture of just a kind of a random polynomial function. And let's observe a few things about the graph of this function, just as a review mostly. Notice that the x-intercepts would be negative 3, looks like 2, and 5. And we would say that the graph crosses through the x-axis at negative 3 and 5, but it touches without crossing at x equals 2. So we may come back to this in just a minute. Let's learn a couple of other terms. All right, well, the graph of every polynomial function of degree n is blank and blank, no sharp corners. In other words, and this is a term that's frequently used, it's smooth, and it has no breaks in it. You could draw it without lifting your pencil, so it's continuous. Okay, something that would not be smooth would be something like this. This is not a polynomial function. It kind of goes up to a point, and I'll even do another one. At this point and this point, that's not considered smooth. So this would not be a polynomial function, nor would something like this, where it was not continuous. Here it's not continuous, here it's not continuous. So I'll cross those out. All right, well, this is not really a mathematical term. I kind of prefer this one, though. It has at most n ups and downs, or at most n minus 1 turning points, where it looks like the function is decreasing and then changes to increasing, and then maybe it changes to decreasing again. Those are turning points. Let me look at what I mean by this. How many turning points does this function have, or how many ups and downs does it have? I like to count the ups and downs just because it happens to be at most this exact number n, the degree of the polynomial. So in this, it's got 1, 2, 3, 4 ups and downs. It's going down and up and down and up. 1, 2, 3, 4. But the turning points, you would start counting them when you reach a peak or a valley. There are only 3 of them. From this direction, we change into this direction, and then we change into this direction, and then we change into that direction. So it's considered 3 turning points, but I like, again, to call it 1, 2, 3, 4 ups and downs. And eventually, every single polynomial function either rises or falls left. When you go really far left on the graph, eventually it either rises or falls. It quits going up and down no matter what. And it rises or falls right as well. And this is called the end behavior. So let's go back to this graph. Well, notice these arrows. Eventually, if you go far enough right, this just continues to go up forever and ever again. It will never come back down. So this one rises right. And when you go to the left, if you're traveling in the left direction, eventually, get through all these ups and downs, eventually it's going up when you move to the left. So this is also going to rise. It rises left as well. So this one rises left and rises right. It could, if this if this had one more turning point and started coming down forever, then it would be falling right. And likewise, it would be, if it turned around here, it would be falling down. And when you're asked in a problem like this to discuss the end behavior, it takes 4 words. For this graph, it would be these 4 words. It rises left, it rises right. So your only possibilities are rise left or fall left, rise right or fall right, when it says discuss the end behavior.